This is our last calculation of our series on determining the area of enclosed region or graphs. So in this one, we actually have one where we're supposed to work with two graphs at the same time. So in the other previous example, we would have one graph and they would give us a region in the form of our x values. So if you are new and you haven't watched those, you can go and check them under my playlist. So it's highly recommended that you start with those at the beginning, then you build up. So here you can see we're actually given two functions. You have f of x and we also have g of x. In this instance, they didn't give us our x values that we have to work with, because we know normally if they give you x value in a function, you can actually be able to draw the function by plotting your table and using those values that they've given you. So from our standpoint, we also comfortable with determining our parent function. So what does the graph of this look like? We know that the graph of x squared is the graph of parabola, which is going to be looking like this. Then what's the graph of this? Remember, this one is our x squared. If I have my root of x, this is the same as having your graph of x to the exponent 1 over 2. Then this, it's a graph that looks like this. So these are mainly the parent function that you have to know. And once again, I would emphasize that you go and watch a video that I made which talks or summarizes all the calculus graphs that you need to know, or basically teaches you how to master all the graphs and how to not forget them. So that's how I said in the beginning, we are already comfortable with determining our parent function, so we don't actually need the values. But if you don't know how the shape looks like, you can always use your range of numbers that you would choose and draw your table. So now if we have these ones that are looking like this, then how are we going to combine them together? Remember, we have this one, which is the x squared. Then if we have that one x, the x squared, then I'm just gonna write the other one in blue, which is this one, I mean to say in green. So it means this one is going to be a graph that looks like that. So now you see the graph, or the part, not the graph, the part that is enclosed by the two, it's mainly this one. So we definitely know the point that is here, which is your 0, 0, but the point that is here, we don't know it. So how can we find that point? Well, we can find that point by finding our intersection. So if we are able to find our intersection, it means now we can be able to find the correct x value for that one. So how do we find our intersection? We find our intersection by combining the, not combining, by equating the two functions together. Meaning I'm going to have what? I have my x squared being equals to the square root of x. So if I want to remove that square root, I have to square both sides. So I have x squared all squared, then I have square root of x all squared. Then this is the same as having your x to the exponent 4 is equals to your x. See? So remember, this is the same as having your inside as your x to the exponent 1 over 2. Then here we have that 2. So for those that don't understand, then this 2 is going to cancel that one, hence that's why I just have that 2. Then in this instance, it's 2 multiplied by 2, then you get this for here. So now you can say, okay, I can actually take this one to the other side and say you have your x to the exponent 4 minus x is equals to 0. Then you know, okay, I see that I have x to the exponent 4 minus x. I can actually take x as the common one. Then you'll say you have x, then you are left with your x to the exponent 3 minus 1. This would be equals to 0. See, since I've taken this out, I will be able to just like work this out. Nice. And remember, if I'm multiplying by this, I should be able to get back to this one. So if I multiply by this, I'm going to get x to the exponent 4. Multiply by this multiply by this, I'm going to get minus x. So now you can say you will have your x being equals to 0, or your x would be equals to 1. So your x being equals to 1, it means now this is the value that we are looking for. So here it means we do have 1. You see, so it means you're going to be working from 0 to 1. 0 to 1 there. You see? So now it means you have to determine which graph it's going to be at the top. To determine this, or just to remember, because I get students who will say, okay, between this graph and this graph, which one, when we're writing the formula, becomes at the top? Because you would find that they've written something like your x squared minus, or your f of x minus your g of x, and they don't know why do they do that instead of saying g of x minus your f of x. They mainly do that because when they go to this part, you mainly look for the one that is on top of which the other one. This, it's your root of x. Then this one, it's the one where you have your x squared. So you always have this one on top minus the other one. So how is that going to look like? So you will say, what do you have? Let me erase this part. So you will say, okay, you have an integral that is between 1 and 0. Then I'm just going to open a bracket that you have your square root of x, which is that function at the top, minus your x squared, which is the one in the bottom. See, then you have what? You have your d of x. And always remember this, it's your value of b, the one, this is your value of b, and this is the value of a. This is known from what? From your fundamental theorem. The value of b, it's always your bigger number. The value of a, it's always your smaller number. Where are we getting this 1 and 0? We're getting this 1 and 0 from our actual graph, which is this region that we are working out. You see, because we are asked to find that area that is enclosed within the graph. So the next step that we have to do is to determine the antiderivative of root of x and also the antiderivative of x squared. So I'm gonna write them here separately, because that's basically how you have to do them. Because if you have this function minus this function, and you're supposed to find the antiderivative, the quickest way it will be to do them separate. So we have x squared. So with your x squared, we know we're going to use the power rule. What does the power rule says? It says if you have an integral of x to the exponent, then this is the same as having your 1 over n plus 1 multiplied by your x to the exponent n plus 1. So your 2 is your n. Remember, you can have a graph where you say you have your x to the exponent n. So now it means if you're going to come here, you will say you have your 1 over 2 plus 1. 2 is that n that I was referring to. So here you will have your x to the exponent 2 plus 1. Then this becomes 1 over 3 multiplied by your x to the exponent 3. this is the same as having your x to the exponent 3 over 3. So it means now the antiderivative for this one, so it's minus x to the exponent 3 over 3. So now we have to figure out the antiderivative for the root of x. So if we're going to be doing a root of x, we're still going to be using the power rule, because remember your root of x can be written as your x to the exponent 1 over 2. Then how are we going to do it in this form? We will say we have 1 over 2 plus 1. Then here we'll just put x, then we have 1 over 2 plus 1. You see, then we know that our 1 over 2 plus 1, it gives us 3 over 2. So this is the same as having 1 over 3 over 2, then multiply by x, then we have 3 over 2. Then this, how do we simplify this? We know we have 1 divided by 3 over 2 multiplied by your x to the exponent 3 over 2. Then this, if we want to solve it, we'll say we have 1 multiplied by, when we multiply it actually flips, we're going to have 2 over 3 multiplied by x to the exponent 3 over 2. You see, so now it means the antiderivative for your square root of x, it's your 2x to the exponent 3 over 2 over 3. So you're going to say you have 2x to the exponent 3 over 2 over 3. Remember, this is over 1. So yeah, just take note of that. We have 2x to the exponent 3 over 3. So that's mainly how you're going to write that one. Then we have to find at which region. We know that we have the region between, let me just do it like this, we have the region between that 1 and 0. So now we have to do the final calculation. So how will the final calculation look like, considering that we have to use the fundamental theorem? So now we'll say we have our 2 into, remember we always have the function of for b minus the function of a from the fundamental theorem. We have 2 into, so we have 1 x cube over 3 minus, we still put 1 cube over 3. So this is 1, then we deduct the 1 for 0. So we're going to have 2 into 0 cube over 3 minus 0 cube over 3. So it's not really necessarily to show this part. You can just leave it out and be left with this 1. You see, then if you solve this one, it will mainly give you something like your 1 over 3. You see, so for those perhaps who are still new with the fundamental theorem, you always have a formula that says you have your b, you have your a, you see you have your f of x is equals to your f of x dx. This will be from the region where you have your b and a. Then how does this simplify? It means we can actually find the function or the difference between the function of b minus the difference between the function of a. This is basically what we were doing this side. So we have our b, which is a bigger number, and a, which is a smaller number. Hence that's why you see the 1 and the 0 here. And the 1 and the 0, I said you get them from this graph. So it would mean if we are taking these numbers and putting them under our fundamental theorem, this would be equals to 0, then this would be equals to that 1. So now is that okay? You are doing the function for 1 minus the function of that one of 0, which is what we were doing there. So always remember, when we're doing this type of calculations, when we get to the antiderivative, we're supposed to use the fundamental theorem in order to get to that final area. And just like in the other videos, I'm still going to emphasize that you do visit that video where I'm teaching all calculus graphs, so that you can also be able to draw these types of graphs without actually having to calculate your function values. And it's actually nice because in calculus, if you know how to draw your functions and you can do your differentiation, you're almost there. I don't see you experiencing a lot of difficulties in the module if you can do that, because now you know that if you know how to differentiate, then it means now you can also do your antiderivatives, because those are just the inverse of one another, you see, because most of the questions is just going to be drawing of your graphs, or you being able to remember your parent function. If you don't know if you don't remember your parent function, they will ask you to do your differentiation, or things like finding your critical points, because you know that's definitely asking you to differentiate, or your chapters where they tell you to tell them where the graph is increasing or decreasing, you still have to do your differentiation. That's where you're doing those first derivatives, you see. So that's one key thing to keep in mind and remember. Master your graphs, master your differentiation, master your integrals, then you're done. The rest is history. So this is the end of the series for these types of graphs. In the next video, we will be looking at something different. Perhaps it could be marginal cost or another different example, but not in these types of graphs where we're finding enclosed areas. So see you in the next video.